Picture this: a silent storm of invisible particles, hurtling through the cosmos at nearly the speed of light, piercing through planets, stars, and even you. These aren't fragments of science fiction. They're real, they're relentless, and they've been bombarding Earth for billions of years. Cosmic rays, one of the universe's most baffling phenomena, arrive from the depths of space carrying secrets we're only beginning to unravel. Some originate from exploding stars, others from black holes, and a few from places so mysterious their very existence defies explanation. What are these enigmatic messengers trying to tell us, and why, after over a century of study, do they still leave scientists scratching their heads? Think about this for a moment. Every second, thousands of these high-energy particles streak through your body, unseen, unfelt, yet packed with enough energy to light up a city. Some cosmic rays are so powerful they shouldn't exist under the laws of physics as we know them. Yet here they are, whispering clues about the darkest corners of the universe, places where matter is twisted into impossible shapes, where energy defies logic, and where the rules of reality seem to rewrite themselves. These aren't just curiosities for astronomers. They're cosmic puzzles that could reshape our understanding of everything from the birth of galaxies to the fabric of space-time itself. That's exactly what we're diving into today. 25 of the most mind-bending, spine-tingling mysteries tied to these cosmic rays. From particles that outpace black holes to signals that might hint at dimensions beyond our own, each one is a story of human curiosity colliding with the unknown. This isn't just a countdown, it's a journey to the edge of what we know and beyond. So buckle up. By the end of this, you'll never look at the night sky the same way again. The story begins in the vast emptiness of space, where an invisible bullet tore through the cosmos at a speed so extreme it defied belief. On October 15, 1991, an observatory in Utah detected something impossible. A single cosmic ray particle carrying the energy of a baseball thrown at 60 miles per hour, all packed into a speck smaller than an atom. Scientists dubbed it the "Oh my God" particle, and for good reason. It was traveling at 99.9% the speed of light, so fast that if it raced a beam of light across the Milky Way, it would lose by barely a hair's breadth after 100,000 years. Think about that: a particle with more energy than anything humans have ever created in a lab, not from a supernova or a black hole, but from somewhere or something utterly unknown. The discovery sent shockwaves through astrophysics. Here's why: according to Einstein's theory, particles this energetic should lose speed as they collide with the faint glow of leftover radiation from the Big Bang. Yet this one didn't. It arrived practically untouched, as if the universe itself had no friction to slow it down. Even stranger, no known cosmic event, no collapsing star, no colliding galaxies, could plausibly produce such a particle. It's like finding a single snowflake with the force of a hurricane. To this day, the "Oh my God" particle remains a mystery. Some theories suggest defects in spacetime itself, cosmic strings snapping like rubber bands, or even particles leaking from other dimensions. But here's the chilling part: it wasn't alone. Since then, dozens more of these ultra-high-energy cosmic rays have been detected, each one a silent alarm bell ringing from the depths of the cosmos. Whatever's hurling them our way doesn't just break the rules, it rewrites them. Deep beneath the frozen wasteland of Antarctica, where temperatures plunge to -100 degrees Fahrenheit and the ice stretches over 2 miles thick, scientists made a discovery that defies logic. Buried under all that ice, specialized detectors picked up cosmic rays unlike anything seen before, particles that seemed to appear from nowhere, with no traceable origin in the known universe. Dubbed the Antarctic anomaly, these cosmic rays don't behave like ordinary high-energy particles. Instead of streaking down from the cosmos above, they blast upward through the Earth itself, as if emerging from the planet's core. How is this possible? The answer lies in the way these particles interact with matter. When typical cosmic rays collide with Earth's atmosphere, they shatter into cascades of secondary particles, all moving downward. But the Antarctic anomaly events show the opposite effect, particles shooting up from below, as if something beneath the ice is generating them, the most baffling part. There's no known physical process inside our planet that could produce such high-energy particles. The experiments designed to catch these anomalies are as extreme as the environment itself. Teams drill deep into the ice to deploy sensors like IceCube, a massive detector array with over 5,000 optical modules frozen in place. These sensors watch for faint streaks of blue light Cherenkov radiation left behind when cosmic rays interact with the ice. It's like trying to find a single spark in a snowstorm. Yet despite the challenges, the data is undeniable. These particles are real and they shouldn't exist. Theories attempting to explain this phenomenon range from the plausible to the downright fantastical. Some scientists propose that dark matter, the invisible substance making up most of the universe's mass, could be decaying in Earth's core, releasing bursts of energy. Others suggest hidden magnetic fields or unknown quantum effects might be redirecting cosmic rays in impossible ways. And then there's the wilder speculation. Could these particles be evidence of parallel universes leaking into ours, or even remnants of a long-dead star's collapse echoing through dimensions we can't perceive? One thing's certain: whatever's causing the Antarctic anomaly, it's rewriting the playbook on how cosmic rays should behave. And if there's one lesson from history, it's that when the universe throws us a curveball this extreme, we're usually on the brink of uncovering something extraordinary. So while the ice keeps its secrets for now, the hunt for answers is far from over. Somewhere in the vast emptiness between galaxies, where darkness stretches for millions of light-years without a single star to break it, cosmic rays are born from nothingness, or so it seems. Astronomers call them galactic ghost rays, high-energy particles that arrive with no visible source, no collapsing star or turbulent nebula to explain their existence. These are cosmic rays without a cosmic address, appearing to emerge from the void itself, and they're forcing scientists to rethink everything we thought we knew about how these particles travel across the universe. Consider this: when we trace the path of most cosmic rays back through space, they usually lead us to violent, energetic events like supernova or active galactic nuclei. But the ghost rays point to nothing, just empty sky. It's as if you followed the trail of footsteps in the snow only to find they vanish mid-stride with no sign of who or what made them. The implications are staggering. Either these particles are coming from sources so faint or distant we can't detect them, or something far stranger is at work, perhaps a phenomenon we haven't even dreamed of yet. One leading theory suggests these ghost rays might be the echoes of ancient cosmic cataclysms, particles that have bounced and twisted through magnetic fields for so long that their true origins are lost to time. Imagine throwing a stone into a winding canyon. By the time the echoes reach you, it's impossible to tell exactly where the sound began. Another, more radical idea proposes that dark matter, the invisible scaffold of the universe, could be decaying in these empty regions, releasing bursts of energy we detect as ghost rays. Then there's the most unsettling possibility of all. What if space isn't as empty as we think? Quantum physics tells us that even a perfect vacuum teems with fleeting particles popping in and out of existence. Could these ghost rays be evidence of something deeper, some fundamental process weaving energy into the fabric of spacetime itself? Whatever the answer, one thing is clear: the universe has a way of hiding its greatest secrets in plain sight, and these phantom particles may be the key to uncovering them. The Sun is supposed to be our cosmic neighbor, a familiar, predictable ball of plasma we've studied for centuries. But when it comes to cosmic rays, our star has a few shocking secrets of its own. Solar flares, those explosive eruptions on the Sun's surface, have long been known to unleash bursts of energy and charged particles, yet something doesn't add up. Hidden in the chaos of these eruptions are cosmic rays with energies so extreme, they defy everything we thought we knew about our own solar system's limits. Take the Carrington event of 1859, the most powerful solar storm ever recorded. It lit up telegraph lines, sparked fires, and painted the skies with auroras as far south as Cuba. But modern analysis reveals something even stranger: traces of cosmic rays embedded in that storm with energies 1,000 times stronger than any solar flare should produce. It's like a campfire suddenly shooting out bullets at the speed of a particle accelerator. The mystery deepens when you look at how these solar-linked cosmic rays behave. Unlike typical solar particles, which follow predictable paths tangled in magnetic fields, these high-energy outliers seem to ignore the rules. They arrive faster, hit harder, and carry bizarre isotopic signatures, hints that they might not originate from the Sun at all, but instead get supercharged by some unseen mechanism lurking between the stars. One theory points to magnetic reconnection, a process where the Sun's magnetic field lines snap and realign, catapulting particles to unimaginable speeds. But even that can't fully explain the energies detected. Another idea suggests these rays might be interstellar hitchhikers, cosmic rays from deep space that get caught in the Sun's outbursts like driftwood swept up in a tidal wave. Whatever the case, the implications are staggering. If our own Sun can unexpectedly produce or amplify particles this powerful, it means we've underestimated the dangers of even routine solar activity. Imagine a future where a single solar flare unleashes a wave of these rogue cosmic rays, bypassing Earth's magnetic shield and frying satellites, disrupting power grids, or even posing risks to astronauts. It's not science fiction, it's a puzzle scientists are racing to solve before the next big solar storm hits. And with every anomalous particle detected, one thing becomes clearer. The Sun still has a few surprises left, and they're rewriting the textbooks one flare at a time. Deep in the shadows of the universe lurks an invisible giant dark matter, the mysterious substance that outweighs all visible stars and galaxies 5-1. We can't see it, we can't touch it, yet its gravitational pull shapes the cosmos. Now, scientists suspect this ghostly material might have a calling card: cosmic rays. Not just any cosmic rays, but bizarre particles with energy signatures that don't match known astrophysical sources. Could these be the fingerprints of dark matter decaying or colliding in the void? The search for this connection centers on an anomaly, an excess of positrons, the antimatter twins of electrons, detected by instruments like the Alpha Magnetic Spectrometer aboard the International Space Station. These positrons stream through space at energies too high to be explained by ordinary cosmic ray interactions. One compelling explanation: dark matter particles annihilating each other in distant space, creating bursts of energy that eventually reach us as these strange cosmic rays. Think of it like hearing echoes in a pitch-black room. You can't see what made the sound, but the vibrations tell you something's there. But proving this isn't so simple. The challenge is separating dark matter's possible signals from cosmic noise. Supernova, pulsars, and other energetic phenomena also produce positrons, muddying the waters. To untangle the mystery, scientists deploy underground detectors like Xenon and LUX, shielded from ordinary cosmic rays by miles of rock, waiting for the faintest flicker of dark matter interaction. Meanwhile, space-based observatories map the positron excess across the sky, searching for patterns, clumps, or directional hints that might point to dark matter's hidden hand. The stakes couldn't be higher. If confirmed, this link would solve two cosmic puzzles at once: the nature of dark matter and the origin of these enigmatic rays. But the universe loves its secrets. So far, every potential dark matter signature could also be explained by more mundane astrophysics. It's like chasing a whisper in a hurricane. Every clue is fragile, every answer provisional. Yet the hunt continues, because if dark matter truly announces itself through cosmic rays, It would be the breakthrough of a lifetime, a direct message from the hidden architecture of reality itself. Among the countless cosmic rays raining down on Earth, a special class stands out not for their speed or energy, but for their sheer strangeness. These are the ultra-heavy nuclei cosmic rays built from elements far heavier than iron, packing an atomic punch so rare that detecting one feels like finding a single grain of sand marked differently in an endless desert. Ordinary cosmic rays are mostly protons or lightweight nuclei, but these outliers containing gold, platinum, even uranium shouldn't exist in such abundance. Yet here they are, arriving from the void with a message we're still struggling to decode. Where do they come from? The universe isn't exactly generous when it comes to crafting heavy elements. They're forged in the most violent events imaginable: neutron star collisions, supernova explosions, or processes so extreme they warp the very laws of nuclear physics. Picture two neutron stars, each a city-sized chunk of matter so dense a teaspoonful weighs as much as a mountain, spiraling toward each other until they collide. The resulting fireball is a cosmic alchemy lab spewing out gold, platinum, and other heavy elements like sparks from a forge. But here's the catch: these elements should condense into dust, not get flung across space as lone, high-speed nuclei. Yet somehow they're escaping and reaching us with energies that defy explanation. Studying them is a feat of patience and precision. Most ultra-heavy nuclei get shredded by interstellar magnetic fields or destroyed in Earth's atmosphere long before they reach detectors. To catch them, scientists rely on instruments like the Cosmic Ray Energetics and Mass Experiment, or CREAM, a balloon-borne observatory floating high above Antarctica. It's like trying to catch bullets with a butterfly net, only these bullets are invisible, vanishingly rare, and might rewrite our understanding of stellar chemistry. The mystery deepens when you examine their energy profiles. Some of these nuclei arrive with such force that their likely origins, neutron star mergers or supernovae, can't fully account for their speed. One theory suggests they're being supercharged by undiscovered cosmic accelerators, perhaps active galactic nuclei with magnetic fields trillions of times stronger than Earth. Another, more radical idea proposes they're remnants of primordial superheavy elements, relics from the early universe that somehow survived annihilation. But the most tantalizing possibility: these ultra-heavy nuclei might be tracing a path to something even rarer, exotic states of matter predicted by quantum theory but never observed, like quark nuggets or strange matter. If true, each detection isn't just a cosmic ray. It's a fragment of a reality we've never seen, hurled at us from the edge of physics itself. And that's what makes this puzzle so thrilling. Every ultra-heavy nucleus that streaks through our detectors isn't just a particle. It's a question waiting to be answered. For decades, cosmic rays followed a predictable pattern: mostly protons, a few heavier nuclei, and barely a trace of antimatter. Then came the shocker, when high-altitude balloons and satellite detectors began counting positrons. They found far more of these antimatter particles than anyone expected. The numbers didn't just inch up, they skyrocketed at energy levels where conventional physics said they should plummet. It was like opening a jar expecting a dozen fireflies and finding a swarm so dense it lit up the room. The first clues emerged from experiments like Pamela, a satellite-based detector that in 2006 began spotting positrons with energies up to 100 gigaelectronvolts, far beyond what typical cosmic ray collisions should produce. Then came the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer, each confirming the anomaly with even higher precision. The message was clear: something out there, something invisible, was flooding the cosmos with these rogue antimatter particles. Scientists immediately split into camps. One group pointed to pulsars, rapidly spinning neutron stars that act as natural particle accelerators, capable of churning out electron-positron pairs in their intense magnetic fields. The Crab Nebula's pulsar, for example, spins 30 times per second, whipping particles to near light speeds. If enough pulsars existed within a few thousand light years, their combined output might explain the excess. But the numbers still didn't quite fit. Pulsars produce positrons in pairs with electrons, yet the observed ratio was lopsided. More crucially, the positron spectrum kept rising at energies where pulsar models predicted it should drop. That's when dark matter theorists seized the opening. Certain hypothetical particles, like weakly interacting massive particles or WIMP, could annihilate each other in space, producing positrons as a byproduct. If dark matter clumped in our galactic halo, these annihilations might precisely match the mysterious surplus. The debate grew fiercer when physicists realized another possibility. The positrons might not be coming from deep space at all. Earth's own magnetic field could trap and re-accelerate stray antimatter, creating a local illusion of excess. Others proposed exotic astrophysical objects colliding neutron stars, microquasars, or even primordial black holes as alternative factories for these particles. Amid the theories, one experiment delivered a bombshell. In 2017, the High-Altitude Water Cherenkov Observatory in Mexico found something peculiar. The positron excess wasn't uniform across the sky. It arrived slightly stronger from one direction, a faint but detectable anisotropy. If the source were dark matter, it should be evenly distributed. But if pulsars were responsible, their uneven locations might explain the lopsided signal. Yet even now, the puzzle refuses to resolve neatly. New detectors like the upcoming all-sky medium-energy gamma-ray observatory promise sharper data. But for the moment, the positron excess remains a cosmic tug-of-war between known astrophysics and the tantalizing unknown. Whether it's dark matter's first whisper or pulsars behaving in ways we don't yet understand, one truth stands out. The universe is balancing its books with antimatter, and we've only just begun to read the ledger. Astronomers have long mapped cosmic rays as a uniform drizzle from all directions until they spotted the anomalies. Hidden in the flood of particles are strange, persistent hotspots, regions of the sky where cosmic rays arrive with such intensity that they defy the laws of chance. These clusters don't match known supernova remnants or active galaxies. Instead, they glow like cosmic bullseyes, hinting at something massive and invisible lurking just beyond our sight. Take the case of the most famous hotspot, located near the constellation Cygnus. Detectors like the Pierre Auger Observatory in Argentina have recorded dozens of ultra-high-energy cosmic rays, all tracing back to this single patch of sky. Statistically, the odds of this happening randomly are less than 1 in 1,000. It's as if you threw confetti into the wind, only to find half of it landed neatly inside a teacup a mile away. One leading theory points to local supernova remnants, the shattered debris of dead stars. The Cygnus region, for instance, houses the sprawling Gamma Cygni Nebula, a graveyard of stellar explosions. But here's the catch. The energies of these hotspot particles exceed what even the most violent supernova should produce. Compounding the mystery, some hotspots don't align with any visible structure at all. They're cosmic blank spots, empty of the usual suspects like pulsars or black holes. Another possibility involves magnetic chaos. Galactic magnetic fields twist and funnel cosmic rays like invisible rivers, potentially concentrating them in certain areas. Yet simulations show this shouldn't create such stark clustering. The hotspots are too intense, too precise. Some researchers speculate they're signposts to hidden accelerators, cosmic megastructures we've yet to discover. Imagine stumbling across footprints in the desert, only to realize they lead to a buried city no map has ever recorded. Then there's the wild card, topological defects. These theoretical kinks in space-time, remnants of the universe's fiery birth, could act as natural particle traps, funneling cosmic rays into bizarrely focused beams. If true, each hotspot might be a fossil from the Big Bang itself, a scar in the fabric of reality that's still bending the rules. Yet for all the theories, the hotspots resist easy answers. Every time a new observatory comes online, whether it's Tibet's Gamma experiment or the planned Cherenkov telescope array, the data only deepens the puzzle. Some hotspots flicker over time, others hold steady for decades. One thing's certain, whatever's creating these cosmic target zones doesn't play by the usual rules. And that's what makes them so thrilling. In a universe that loves uniformity, hotspots are the outliers, the rogue signals whispering that there's still so much we don't understand. Time bends under extreme conditions, a fact Einstein proved over a century ago. But what if some cosmic rays don't just obey relativity's rules? What if they twist them? Enter the most mind-bending cosmic rays of all, particles so energetic they might literally outrun time itself. At energies exceeding 10 to the 20th power electron volts, millions of times stronger than anything humans can produce in particle colliders. These rays approach the speed of light so closely that relativity's strangest effects kick in. For them, time slows to a crawl, distances shrink to nothing, and the very fabric of reality warps in ways that challenge our understanding of cause and effect. Take one of these ultra-relativistic particles, let's call it a time traveler ray, as it streaks across the universe. From our perspective here on Earth, the journey might take millions of years. But for the particle, thanks to time dilation, its internal clock might tick only a few seconds between creation and detection. It's like watching a high-speed bullet frozen in midair while the world around it rushes forward in fast motion. The implications are staggering. If these rays could perceive their own existence, they'd experience the cosmos as a fleeting blur, with galaxies forming and dying in what feels like an instant. The real mystery lies in their origins. To reach such insane speeds, something must accelerate these particles harder than any known natural process. Black holes colliding galaxy clusters, or perhaps something more exotic, cosmic strings, theoretical defects in spacetime left over from the Big Bang, snapping like rubber bands and flinging particles across eternity. Some physicists even speculate these rays might be tapping into hidden dimensions where the laws of physics permit energies we can't yet imagine. But here's where it gets wilder. If time dilation distorts these particles' experience of reality, could they carry information from the distant past or even the future? Quantum mechanics allows for particles to exist in probabilistic states until observed. Could ultra-relativistic cosmic rays be entangled with their own past or future selves, creating feedback loops in time? It sounds like science fiction, but the math doesn't rule it out. Experiments like the telescope array in Utah have detected rays with energies so high they shouldn't exist in our current universe without some fundamental revision of physics. The hunt for answers pushes detectors to their limits. When a time-dilated cosmic ray hits Earth's atmosphere, it creates a particle shower so vast it can light up sensors across dozens of square miles. Observatories like the Pierre Auger array in Argentina map these cascades with pinpoint precision, tracing each ray's path back to its source. Yet the more data we collect, the clearer it becomes. These particles aren't just breaking records, they're bending the rules of existence. One theory suggests they're relics of the early universe, frozen in near light-speed flight since the first moments after the Big Bang. Another proposes they're messengers from civilizations far beyond our own, harnessing energies we can't yet comprehend. But the most humbling possibility, these rays might be showing us that time itself isn't what we think, that at the universe's extremes, past, present, and future blur into something far stranger. Every detection is a ripple from the edge of reality, a reminder that the cosmos still holds mysteries beyond our wildest imagination. The universe beyond our galaxy doesn't just send us light, it fires bullets. Some cosmic rays arrive with such staggering energy that they couldn't possibly have originated within the Milky Way. These extragalactic invaders, as scientists call them, pack enough punch to cross millions of light years, dodging magnetic fields and galactic winds, only to slam into Earth's atmosphere with the force of a meteor strike. But here's the catch. Tracing their origins is like trying to find a single flashlight in a pitch-black city the size of a continent. Take the case of the highest energy cosmic rays ever detected, particles with energies exceeding 100 exaelectronvolts, billions of times more powerful than anything produced in particle colliders. When these extraterrestrial bullets hit our atmosphere, they trigger particle showers so vast they can light up detectors across 30 square miles. Yet despite their incredible energy, their sources remain maddeningly elusive. Unlike light, which travels in straight lines, cosmic rays get twisted and scrambled by magnetic fields as they journey through space. By the time they reach us, their paths are so tangled that pointing back to their origins is nearly impossible. This cosmic game of hide and seek has led scientists to some startling possibilities. One prime suspect: active galactic nuclei, the monstrous cores of distant galaxies where supermassive black holes devour matter and spew out jets of radiation. These cosmic furnaces could accelerate particles to unimaginable speeds, launching them across intergalactic space like a celestial slingshot. Another candidate: colliding galaxy clusters, where shock waves from merging behemoths might create natural particle accelerators spanning millions of light years. But the plot thickens. Some extragalactic cosmic rays don't seem to line up with any known structures at all. They appear to come from voids, vast, empty regions of space where few galaxies exist. This has sparked wilder theories, like decaying dark matter or even defects in spacetime itself flicking particles across the cosmos like cosmic pinballs. The implications are profound. If these rays truly originate from nowhere, it suggests our map of the universe's most violent events is missing entire chapters. Detecting these intergalactic messengers requires ingenuity. Observatories like the Pierre Auger Array in Argentina use thousands of water tanks to catch the faint afterglow of particle showers, while space-based instruments like the JM-USO experiment aim to spot the ultraviolet flashes these rays produce as they streak through the atmosphere. Each detection is a breadcrumb, a clue hinting at the invisible maelstroms shaping the cosmos beyond our galactic doorstep. What's at stake isn't just the mystery of these particles, it's a window into the universe's most extreme environments. Every extragalactic cosmic ray is a postcard from a place where physics operates at its limits, where black holes twist spacetime into knots and galaxies collide in explosions of raw energy. And while their origins remain shrouded in mystery, one thing is certain: these invaders from beyond the Milky Way are rewriting what we thought we knew about the universe's hidden chaos. There's a line in physics beyond which particles aren't supposed to go, a cosmic speed limit set by the universe itself. But some cosmic rays don't just cross that line, they obliterate it. These are the forbidden particles, cosmic rays with energies so incomprehensibly high that their very existence mocks our current understanding of reality. According to the most trusted models, particles shouldn't be able to reach these energy levels without unraveling the fabric of spacetime. Yet here they are, slamming into Earth's atmosphere with the force of a bowling ball dropped from space, packed into a single subatomic speck. The puzzle starts with something called the Greisen-Zatzeping, Kuzmin, or GZK cutoff. Named after the physicists who predicted it, this theoretical barrier states that ultra-high-energy cosmic rays traveling across intergalactic space should hit a wall, literally. The universe isn't empty, it's filled with the faint glow of cosmic microwave background radiation, remnants of the Big Bang. When a particle approaches energies beyond 10 to the 20th power electronvolts, it should collide with these background photons, losing energy like a marathon runner crashing into a windstorm. The math is clear: no cosmic ray should reach Earth with energy above this limit, except they do. Detectors like the Telescope Array in Utah and the Pierre Auger Observatory in Argentina have repeatedly spotted cosmic rays blasting past the GZK cutoff as if it doesn't exist. It's like finding a car that somehow drives faster than its own engine should allow, defying every known law of mechanics. These particles aren't just breaking records, they're exposing gaps in our fundamental grasp of how the universe works. So where do they come from? One radical theory suggests these rays might be tapping into hidden dimensions, extra layers of reality predicted by string theory, where the usual rules of physics don't apply. In these unseen dimensions, particles could accelerate unimpeded, bypassing the GZK cutoff entirely before leaking back into our observable universe. Another idea points to cosmic defects, kinks or tears in space-time left over from the universe's fiery birth. If these defects snap or vibrate, they might release bursts of energy capable of launching particles beyond theoretical limits. Then there's the most unsettling possibility. These forbidden rays might be proof that relativity, Einstein's cornerstone theory, needs an update. At energies this extreme, space and time could behave in ways we've never anticipated, warping the rules just enough to let these particles slip through. Imagine discovering that gravity sometimes pushes instead of pulls. It's that level of paradigm shift. What makes these cosmic rays so thrilling isn't just their defiance of physics. It's what they represent, a beacon from the unknown, signaling that the universe still holds realms beyond our imagination. Every detection is a challenge, a dare from nature itself to rethink what we're certain we know. And until we solve their riddle, one thing's clear: the cosmos isn't just playing by its own rules. It's rewriting them in real time. Among the countless particles racing through the cosmos, neutrinos stand apart, ethereal, nearly massless, and so reluctant to interact with matter that trillions pass through your body every second without a trace. Yet these ghostly particles might hold the key to one of cosmic rays' greatest puzzles, where their unimaginable energies come from. Unlike cosmic rays, which get twisted off course by magnetic fields, neutrinos travel in perfect straight lines from their birthplaces, pointing back to their origins like cosmic arrows. When ultra-high-energy cosmic rays collide with interstellar gas or radiation, they produce cascades of particles, including neutrinos. Catch one of these neutrinos, and you might just trace it back to the cosmic accelerators we've been searching for. The first clues emerged from deep beneath the Antarctic ice. In 2013, the IceCube Neutrino Observatory detected two neutrinos with energies so extreme they earned the nickname Bert and Ernie. These weren't your average solar neutrinos, they carried over 1,000 times more energy, hinting at violent origins like supermassive black holes or colliding galaxies. But the real breakthrough came when researchers cross-referenced their arrival directions with cosmic ray data. One lined up with a blazar, a galaxy powered by a voracious black hole spearing the cosmos with jets of radiation, suggesting these neutrino factories might also be the birthplaces of ultra-high-energy cosmic rays. Here's why this link matters. Cosmic rays and neutrinos are two sides of the same explosive coin. When cosmic rays accelerate near black holes or other extreme environments, they smash into surrounding matter, creating pions, unstable particles that decay into both gamma rays and neutrinos. Detect the neutrinos and you've found the hidden footprint of cosmic ray production. It's like hearing the echo of a distant explosion and using it to pinpoint the blast site, even if the original fireball is obscured by cosmic dust. The search for these connections is pushing detectors to their limits. IceCube, with its frozen grid of sensors, watches for the faint blue flashes neutrinos leave as they rarely interact with the ice. Upcoming projects like the Cubic Kilometer Neutrino Telescope will expand this hunt to the Mediterranean Sea, turning Earth itself into a giant neutrino trap. Meanwhile, observatories like the High-Altitude Water Cherenkov Gamma Ray Observatory scan the skies for matching gamma ray bursts, the telltale sparks of cosmic ray collisions. But the neutrino cosmic ray partnership isn't just about tracing origins, it's a window into physics at energies we can't replicate on Earth. some high-energy neutrinos appear to arrive with slight delays, a potential hint that spacetime itself behaves differently at these extremes, subtly warping the particle's path. Others exhibit flavors electron, muon, or tau, in ratios that don't match predictions, suggesting unknown particle interactions in their violent birthplaces. The most tantalizing possibility: neutrinos might be the only particles surviving from cosmic events so ancient their light hasn't yet reached us. While photons get absorbed or scattered over billions of years, neutrinos stream freely across the ages, carrying snapshots of the universe's most hidden cataclysms. Every high-energy neutrino we catch isn't just a clue to cosmic rays. It's a whisper from the darkest, most energetic corners of existence, and we're finally learning how to listen. Some cosmic rays don't just arrive, they linger. Imagine a signal bursting through the void, fading into silence, only to return moments later like a cosmic déjà vu. These are the echoes, the rare and perplexing cases where detectors pick up what appears to be the same cosmic ray twice. Not as a continuous stream, but as distinct pulses separated by milliseconds or even minutes, like thunder rolling back after the lightning's gone. At first dismissed as instrument glitches, these delayed signals are now forcing scientists to confront a startling possibility. The universe might be playing tricks with time itself. Take the case of the doublet cosmic rays detected by the telescope array in Utah. In 2017, sensors recorded two ultra-high-energy particles striking the same patch of desert less than a second apart, their energy profiles nearly identical. Statistically, the odds of two unrelated cosmic rays hitting within a square mile in such rapid succession are astronomically low, like tossing a pair of dice and getting snake eyes 1,000 times in a row. Yet this wasn't an isolated incident. From Antarctica to the high Andes, similar echoes have surfaced in datasets spanning decades, each one defying easy explanation. One theory points to atmospheric anomalies. When a primary cosmic ray slams into Earth's upper atmosphere, it triggers a cascade of secondary particles, a phenomenon well documented. But under rare conditions, some of these particles might get trapped in magnetic pockets or scattered by high-altitude turbulence, creating delayed afterimages of the original event. Think of it like shouting into a canyon and hearing the echo bounce back, only here the canyon is Earth's own volatile atmosphere. Then there's the far more radical explanation: space-time hiccups. Quantum gravity models suggest that at unimaginably small scales, the fabric of reality might foam with tiny, ephemeral wormholes or bubbles of distorted time. A cosmic ray skimming the edge of one of these quantum fluctuations could, in theory, arrive in split installments, the particle's own timeline, momentarily tangled by the universe's underlying froth. It's as if the ray passed through a cosmic funhouse mirror, emerging stretched or duplicated, but the most tantalizing echoes come from beyond our atmosphere. In 2021, the IceCube Neutrino Observatory noted a bizarre pattern: high-energy neutrinos arriving in clusters, their timestamps too precise to dismiss as coincidence. Some researchers speculate these could be lensed signals particles bent by the gravity of invisible dark matter clumps or even primordial black holes, their paths warped so severely that the same neutrino appears to strike detectors multiple times along its twisted trajectory. Skeptics argue these echoes are mere artifacts, glitches in detectors, or statistical flukes amplified by confirmation bias. Yet as instruments grow more sensitive, the anomalies persist. If they're real, the implications rewrite cosmic rulebooks. Echoes could hint at hidden dimensions, cracks in relativity, or even evidence of a holographic universe where information isn't lost but reverberates like ripples on a pond. Every repeated signal is a riddle wrapped in the enigma of deep space, and solving it might require physics we've yet to invent. So the next time a cosmic ray whispers twice, listen closely. The universe rarely repeats itself without reason. Physics has boundaries, or at least it's supposed to, but when it comes to cosmic rays, the universe keeps ignoring the rulebook. Scientists long ago calculated a theoretical ceiling for how energetic these particles should get, a limit imposed by the very fabric of space-time. Called the Greisen-Zatsepin-Kuzmin cutoff, this barrier should stop cosmic rays from reaching energies beyond 10 to the 20th power electronvolts. The logic is airtight. As particles approach this threshold, they'd lose energy by colliding with photons from the cosmic microwave background, the afterglow of the Big Bang. It's like trying to sprint through molasses. The faster you go, the more resistance you face. Except cosmic rays didn't get the memo. Detectors have repeatedly spotted particles laughing in the face of this limit. The most famous, dubbed the "oh my god" particle, packed an unprecedented 150 exa-electronvolts of energy, equivalent to a baseball moving at 60 miles per hour, crammed into a single proton. If the GZK cutoff were a wall, this particle didn't just climb over it, it vaporized the bricks on impact, and it wasn't a fluke. From Utah's telescope array to Argentina's Pierre Auger Observatory, ultra-high-energy outliers keep appearing, each one a defiant middle finger to theoretical physics. So what's going on? One possibility is that these rays aren't traveling as far as we think. If they originate within our local galactic neighborhood within a few million light-years, they might not have encountered enough microwave photons to bleed off energy. But here's the twist. The sky maps don't show any obvious sources nearby capable of producing such violence. The other, more thrilling explanation: our understanding of particle physics is incomplete. Some theorists point to exotic acceleration mechanisms, like cosmic strings, hypothetical defects in spacetime from the universe's birth, acting as celestial slingshots. Others suggest hidden dimensions might offer shortcuts, allowing particles to bypass the usual energy-draining collisions. Then there's the radical notion that relativity itself needs an update at these extremes, that spacetime behaves differently when stretched to its limits. Imagine a car that somehow gets better mileage the faster it goes. It defies logic, yet these cosmic rays suggest nature might have loopholes we've yet to imagine. The implications are staggering. If the GZK cutoff isn't absolute, it means the universe hosts accelerators beyond anything we've dreamed of: black holes spinning at near light speed, dark matter annihilations in the void, or even processes we haven't named yet. Every ultra-high-energy cosmic ray that breaches this non-existent barrier isn't just a particle. It's a crack in the foundation of modern physics, inviting us to rethink what's possible. And until we solve the riddle, one thing's clear: the cosmos doesn't just play by its own rules, it scribbles them in invisible ink and dares us to read between the lines. What if some cosmic rays aren't natural at all? Among the countless particles raining down from space, could a handful be messages, or even signatures of intelligence beyond Earth? It's a wild idea, but not one scientists dismiss outright. When ultra-high-energy cosmic rays arrive with patterns that defy conventional explanations, even the most skeptical researchers admit the possibility, however slim, that we might be glimpsing something more than stellar accidents. Take the case of certain particle showers detected by the Havre-Park Array in the 1980s. A handful of events stood out not just for their energy but for their bizarrely timed arrivals. Instead of random intervals, these rays came in clusters separated by precise mathematical ratios, almost like a coded sequence. Was it cosmic static or something more deliberate? The scientific community erupted into debate. Mainstream astrophysicists pointed to rare but natural pulsar behaviors, while a vocal minority whispered about particle beacons, hypothetical alien transmitters using cosmic rays as interstellar Morse code. The logic isn't entirely far-fetched. Cosmic rays have unique advantages as communication tools. Unlike radio waves, which scatter and fade over light years, high-energy particles barrel through dust clouds and magnetic fields with barely a deflection. A sufficiently advanced civilization might see them as the universe's ultimate broadband, capable of piercing galactic distances without degradation. Even the energy requirements, while staggering, aren't impossible for a Kardashev Type 2 civilization harnessing the power of a star. Imagine a neutron star repurposed as a particle cannon, its unimaginable magnetic fields tuned to fling encrypted protons across the cosmos. But here's why most scientists remain unconvinced. For one, natural cosmic accelerators like quasars or colliding galaxies can already produce particles with energies that resemble artificial signatures. Without a repeatable pattern or accompanying electromagnetic signal, it's nearly impossible to distinguish a deliberate transmission from cosmic chaos. Then there's the sheer inefficiency. Blasting messages via cosmic rays would require energies equivalent to supernova, a wildly impractical way to say hello compared to focused radio or laser signals. Yet the hunt for anomalies continues. Projects like Breakthrough Listen now include cosmic ray data in their search for extraterrestrial intelligence, scanning for statistical oddities that might hint at design. And while the odds are vanishingly small, the mere possibility forces us to confront a thrilling question. If the universe is teeming with life, how would we recognize its handiwork? Every unexplained cosmic ray could be a natural wonder, or the first page of a letter we're only beginning to read. The truth, as always, lies somewhere between the known and the unimaginable. At the subatomic level, reality behaves in ways that defy common sense. Particles existing in multiple states at once, information teleporting across distances, and events unfolding differently depending on whether we observe them. Now imagine cosmic rays, the universe's most energetic particles, crashing into this delicate quantum dance. Could these high-speed interlopers be stirring the pot, nudging quantum systems toward unpredictability, or even playing a role in the mysteries of consciousness itself? The answers might rewrite our understanding of reality's deepest layers. Consider quantum decoherence, the fragile process where quantum systems lose their superposition and collapse into definite states. In labs worldwide, scientists shield quantum computers from even the faintest vibrations or electromagnetic whispers to preserve coherence. Yet cosmic rays, packing billions of times more energy than these lab-bound particles, constantly bombard Earth unnoticed. A single high-energy cosmic ray striking a quantum system could act like a bull in a china shop, disrupting delicate superpositions in ways we're only starting to measure. Experiments with superconducting qubits have shown that cosmic rays can indeed trigger sudden decoherence, introducing errors that even the most advanced shielding struggles to block. It's as if the universe itself is whispering. True quantum isolation might be impossible in a cosmos buzzing with invisible particle storms, but the rabbit hole goes deeper. Some theorists speculate that cosmic rays might not just disrupt quantum systems, they could actively shape them. The brain, for instance, operates at scales where quantum effects might play a role in consciousness. While mainstream neuroscience remains skeptical, provocative studies suggest cosmic ray interactions with neural microtubules, tiny protein structures, could influence cognitive processes. Could these high-energy particles, by triggering quantum state changes in brain matter, contribute to the flickers of intuition, creativity, or even random thoughts? It's a fringe idea, but one that bridges the gap between cosmic-scale physics and the inner workings of the mind. Then there's the wild card, cosmic rays as quantum messengers. Entanglement, the eerie link between particles that persists across vast distances, is a cornerstone of quantum theory. If cosmic rays originate from extreme environments like black holes or neutron stars, where space-time warps beyond recognition, might they carry imprints of quantum entanglement from their birthplaces? A particle forged in the whirlpool of a collapsing star could, in theory, remain entangled with its distant twin, meaning every cosmic ray striking Earth might be half of a conversation we're only beginning to decode. The implications spiral outward. If cosmic rays influence quantum systems, could they subtly alter the outcomes of chemical reactions, mutation rates in DNA, or even the evolution of life? Some researchers point to periods of heightened cosmic ray flux coinciding with evolutionary leaps, though the evidence remains hotly debated. Others suggest these particles might seed quantum fluctuations in the early universe that later blossomed into galaxies, making cosmic rays not just passengers in the cosmos but silent architects. What makes this frontier so electrifying is its sheer unpredictability. Every time a cosmic ray pierces a cloud chamber or a quantum detector, it's not just leaving a trail of ions, it's offering a glimpse into a world where the boundaries between particle physics, biology, and philosophy blur beyond recognition. Whether these particles are rogue disruptors or hidden conductors in nature's grand symphony, one truth emerges: the universe speaks in quantum whispers, and cosmic rays might be its most enigmatic translators. The cosmic rays we detect every day seem steady, a predictable drizzle from the void. But sometimes the skies open up and Earth gets caught in a full-blown cosmic storm. These aren't just minor upticks in particle counts. They're sudden, violent surges where detectors worldwide light up like fireworks on the 4th of July, recording fluxes 100 or even 1,000 times higher than normal. The weirdest part, many of these storms arrive without warning, untethered to any obvious cosmic catastrophe. One of the most dramatic spikes occurred in the year 775. Ancient tree rings from that period reveal a staggering spike in radioactive carbon-14, a telltale signature of cosmic rays flooding Earth's atmosphere. For years, historians puzzled over the cause. Then, astronomers found the culprit, a nearby supernova, likely visible in daylight for weeks, its shockwave bombarding our planet with particles. But not all storms have such clear origins. In February 1956, monitors in Sweden, New Mexico, and India simultaneously recorded a cosmic ray surge so intense, it briefly drowned out all other signals. No supernova was seen. The sun, usually a prime suspect, was eerily quiet. To this day, the event remains unexplained, a ghostly tempest with no visible storm cloud. Solar activity plays a role in some of these outbursts, but not the way you'd expect. During the sun's 11-year cycle, its magnetic field waxes and wanes, creating a protective bubble around the solar system that deflects many cosmic rays. Oddly, when solar activity peaks, cosmic ray detections on Earth actually drop. But when the sun quiets, that shield weakens and more particles slip through. The twist: some of the fiercest cosmic storms coincide not with the sun's calm phases, but with its most violent eruptions. Solar flares can blast open temporary gateways in Earth's magnetic field, allowing cosmic rays to funnel in like water through a burst dam. Then there are the rogue wave storms that defy all patterns. In October 2022, detectors in Antarctica and Tibet caught a bizarre 30-minute surge of ultra-high-energy particles. These weren't your typical cosmic rays. Their energy profiles suggested they'd been accelerated by something far more powerful than a supernova. One theory points to starburst galaxies, colliding galaxies where star formation runs rampant, creating chaotic magnetic fields that act like cosmic particle slingshots. Another possibility: gamma-ray bursts, the universe's most violent explosions, might fire off particle beams that sweep past Earth like lighthouse beams, delivering fleeting but intense downpours. The implications of these storms stretch far beyond astronomy. During major events, airline passengers and crews on polar routes can receive radiation doses equivalent to multiple chest X-rays in a single flight. Satellites with no atmosphere to protect them risk critical malfunctions when particle floods overwhelm their circuits. Some researchers even speculate that past cosmic storms might have triggered lightning sprees, setting off wildfires or altering weather patterns. But the biggest mystery remains: what's brewing out there that we haven't seen yet? Hidden black holes, dark matter annihilations, or something entirely new? Every time a cosmic storm hits, it's a reminder that the universe doesn't just whisper, sometimes it screams, and we're only beginning to learn how to listen. Our galaxy should be familiar territory, a cosmic neighborhood we've mapped in exquisite detail. Yet hidden in the flood of cosmic rays from the Milky Way are particles that don't belong. These misfits arrive with energies and trajectories that point unmistakably to our own galactic backyard. But when astronomers trace their paths backward, the trail vanishes into darkness. No supernova remnants, no pulsars, no black holes, just empty space where a cosmic accelerator ought to be. It's like hearing laughter in your house when you're certain you're alone. The first clues emerged from observatories like Hawk, the high-altitude water Cherenkov array in Mexico. Scanning the galactic plane for gamma rays, cosmic rays, telltale byproducts, researchers spotted hotspots with no visible engines. One glaring example lies near the constellation Gemini, where particles stream in with energies up to 100 tera-electronvolts, enough to power a city for seconds if harnessed. Yet the region appears eerily quiet, devoid of the supernova shockwaves or spinning neutron stars that usually crank particles to such extremes. The contradiction is so stark that scientists have dubbed these zones dark accelerators, ghostly machines churning out cosmic rays without leaving a trace. What could these hidden powerhouses be? One leading theory points to corpses of dead stars too faint to see. When massive stars explode, they don't always leave behind the glowing nebulae we associate with supernova. Some collapse into cold, fast-spinning neutron stars with weakened magnetic fields, cosmic zombies emitting little light but still capable of accelerating particles through their rapid rotation. Others might vanish entirely into black holes so isolated, their gravity wells go unnoticed until a stray cosmic ray betrays their presence. Then there's the dark matter angle. If the Milky Way's halo is thick with these invisible particles, as most cosmologists believe, their occasional collisions could produce bursts of energy detectable as cosmic rays. Unlike supernova, dark matter annihilations wouldn't glow in telescopes, they'd be silent eruptions in the void, detectable only by their particle shrapnel. It's a tantalizing possibility, though critics note these signals could also come from mundane sources like undetected gas clouds collapsing under their own gravity. The hunt has driven astronomers to creative extremes. Some teams are stitching together decades of radio telescope data, searching for faint, fast-fading remnants of long-dead supernova. Others are deploying AI to scour gamma-ray maps for subtle patterns, clusters, or asymmetries that might hint at hidden magnetic traps or rogue black holes drifting unseen. The most daring proposal, a space-based observatory called MS-100, designed to catch cosmic rays with such precision that their paths could be traced back to within a fraction of a degree, turning the entire galaxy into a particle crime scene. What makes this mystery so electrifying is its intimacy. These aren't distant intergalactic invaders, they're hometown particles born in the Milky Way's shadowy corners. Every unexplained cosmic ray is a clue that our galactic map has gaps, that monsters might lurk in the darkness between the stars. And until we find them, one thing's certain: the universe's most powerful accelerators aren't just in the spectacular explosions we see. They're in the voids we don't. Imagine throwing a ball against a wall, only to watch it bounce back not just once, but from multiple angles you never aimed for. Now replace the ball with a cosmic ray and the wall with the tangled magnetic fields of our galaxy, and you've got one of the most confounding puzzles in astrophysics. Scientists call it cosmic ray mirroring, a bizarre phenomenon where these high-energy particles don't just travel straight through space. They ricochet, twist, and even double back in ways that defy every simulation. It's as if the galaxy itself is playing an endless, invisible game of pinball with matter, and we're only now catching glimpses of the flippers. The mystery starts with what we think we know. Cosmic rays should follow the Milky Way's magnetic fields like cars on a highway. their paths gently curving as they navigate interstellar twists and turns. But detectors here on Earth keep catching rays that seem to have taken impossible detours, particles arriving from directions that require them to have looped, U-turned, or zigzagged through magnetic labyrinths with no clear exit. The most head-scratching cases involve cosmic rays with nearly identical energies appearing to come from opposite sides of the sky, as if the same particle split in two or bounced off some cosmic backboard. One striking example came from the Pierre Auger Observatory, where researchers traced a cluster of ultra-high-energy rays back to a region near the constellation Centaurus. The twist, some particles pointed toward Centaurus A, a known galaxy with a monstrous black hole, while others seemed to originate from empty space directly opposite their expected path. The only explanation, somewhere along the way, these rays got flung backward by magnetic fields far stronger or more chaotic than our models predict. So why don't our simulations account for this? The answer lies in the galaxy's hidden scaffolding. We've long assumed the Milky Way's magnetic fields are relatively orderly, like the gentle ripples on a pond. But what if they're more like boiling water, full of unpredictable eddies and whirlpools? Areas near supernova remnants or turbulent gas clouds could harbor magnetic knots capable of slingshotting particles in wild directions. There's even speculation that dark matter, invisible and pervasive, might warp these fields in ways we can't yet measure, creating unseen mirrors that catch and fling cosmic rays like light in a hall of mirrors. The implications ripple outward. If magnetic mirroring is more common than we thought, it could upend how we trace cosmic rays to their origins. A particle detected near Earth might seem to hail from a distant quasar when in reality, it's the cosmic equivalent of a bullet that's bounced off three walls before hitting the target. This wouldn't just muddy our maps of high-energy accelerators, it might explain why some cosmic rays appear to come from voids or defy the GZK cutoff. They're not breaking the rules, they've just taken a detour through the galaxy's hidden funhouse. New instruments hope to untangle the chaos. The Square Kilometre Array, a next-generation radio telescope, will map the Milky Way's magnetic fields in unprecedented detail, revealing the mirrors we've missed. Meanwhile, space missions like NASA's Interstellar Mapping and Acceleration Probe aim to track cosmic rays in real time, watching as they interact with local magnetic fields. Every reflection, every unexpected bounce is a clue, not just about the particles themselves, but about the invisible forces sculpting our galaxy's secret topography. What makes this puzzle so thrilling isn't just the science, it's the reminder that even in our own cosmic backyard, the universe still holds surprises. The Milky Way isn't just a stage for cosmic rays, it's an active participant twisting their paths into riddles we're only beginning to decode. And until we solve them, every mirrored particle is a whisper from the dark. The map we thought we knew might still be missing whole dimensions. The invisible rain of cosmic rays doesn't just light up detectors, it might be quietly shaping life itself. Every second, high-energy particles from distant supernova and black holes slice through Earth's atmosphere, piercing plants, animals, and even your DNA. While most pass harmlessly, the occasional extreme cosmic ray could act like a microscopic lightning bolt, scrambling genetic code or frying electronics with consequences that ripple through history. Take mutation rates. In labs, scientists have bombarded organisms with radiation to mimic cosmic rays, observing how these particles break DNA strands and induce mutations. Out in the wild, studies of ancient tree rings reveal spikes in carbon-14, a telltale sign of past cosmic ray surges that align with periods of rapid evolutionary change. The Cambrian explosion, a geologic era 500 million years ago when life suddenly diversified into countless new forms, coincides with evidence of intense galactic cosmic ray activity. Could these particles have been nature's mutagen, jolting evolution into overdrive? It's a controversial idea, but one that gains traction every time astronomers discover a new link between cosmic radiation and genetic instability. Then there's technology's fragile dance with these particles. In 2003, a single cosmic ray triggered a voting machine error in Belgium, flipping a candidate's tally mid-election. A year later, another rogue particle altered the flight controls of a commercial airliner mid-flight, forcing an emergency landing. These events, dubbed single-event upsets, are now a known hazard for everything from smartphones to satellites. Engineers armor critical systems with lead and error-correcting software, but as cosmic rays grow more energetic or as Earth's magnetic shield weakens during solar minima, the risks escalate. Imagine a future where a rare ultra-high-energy cosmic ray wipes the memory of a spacecraft orbiting Mars, or worse, triggers a false positive in nuclear early warning systems. The line between cosmic curiosity and global crisis is thinner than we'd like to admit. History hints at even darker possibilities. The year 536 CE was dubbed the worst year to be alive by historians. Global temperatures plummeted, crops failed, and societies collapsed, all amid eerie reports of a dimmed sun and strange atmospheric phenomena. Ice cores from that period show a startling spike in beryllium-10, a radioactive isotope produced when cosmic rays slam into Earth's atmosphere. The leading theory, a nearby supernova or gamma-ray burst bathed the planet in particle radiation, shredding the ozone layer and unleashing cascading climate disasters. Similar events might explain the sudden decline of the Akkadian Empire 4,000 years ago or the year without summer in 1816. Yet cosmic rays aren't just agents of chaos, they might also be silent guardians. Some researchers propose that these particles, by constantly bombarding Earth's atmosphere, generate a low-level ionizing background hum that stimulates biological repair mechanisms. Without this subtle radiation pressure, life might grow sluggish, like muscles atrophying without exercise. There's even evidence that cosmic rays influence cloud formation, potentially regulating Earth's climate over millennia. The deeper we dig, the clearer it becomes. Cosmic rays aren't just interstellar trivia. They're threads woven into the fabric of life's story, tugging at DNA, flickering through our machines, and occasionally rewriting history in bursts of invisible energy. Whether as catalysts for change or unseen saboteurs, their fingerprints are everywhere, if you know where to look. And as our world grows more interconnected, more reliant on fragile technology, their whispers might soon become shouts we can't afford to ignore. Among the thunderous blasts of ultra-high-energy cosmic rays, there's a whisper, a faint, almost ghostly signal so soft it nearly vanishes into the background hum of the universe. These are the ultra-low-energy cosmic rays, particles drifting through space with energies millions of times weaker than their extreme counterparts. While they lack the flashy devastation of the oh my god particle or the Antarctic anomaly, these quiet intruders might hold the keys to something far grander, the hidden architecture of the cosmos itself. Detecting them is like trying to hear a single raindrop in a hurricane. Most cosmic ray observatories are built to catch the universe's loudest crashes, but these whispers slip through their nets. Specialized instruments like the Voyager probes drifting beyond our solar system or the diminutive Alpha Magnetic Spectrometer on the International Space Station are among the few sensitive enough to pick them up. What they've found is startling. These feeble particles don't just meander randomly, they carry imprints of the vast, invisible structures they've traversed. The magnetic tendrils of galaxy clusters, the shock waves of colliding galactic superstructures, even the faint pressures of dark matter's gravitational tides. Here's why that matters. Space isn't empty. It's threaded with a cosmic web, a labyrinth of filaments made of gas, dark matter, and magnetic fields stretching between galaxies. We can't see this web directly, but ultra-low-energy cosmic rays act like subatomic breadcrumbs, tracing paths through its twists and turns. As these particles drift, the web's magnetic fields nudge them subtly, leaving fingerprints in their arrival directions and energies. It's the equivalent of tracking a feather's path to map the unseen currents of wind in a canyon. Some of the most tantalizing clues come from anomalies in these whispers. Certain patches of the sky emit more low-energy particles than expected, hinting at dense knots in the cosmic web where galaxies are born. Others show puzzling voids, regions where rays seem to avoid, as if repelled by some unseen force. One theory suggests these voids might be the footprints of ancient quasars, their long-dead magnetic fields still echoing through space. Another posits that dark energy, the mysterious force accelerating the universe's expansion, could be stretching these particle paths into strange new patterns. Then there's the grandest possibility of all. If we could map these whispers with enough precision, we might finally glimpse the universe's largest-scale magnetic fields, structures so vast they span hundreds of millions of light-years. These fields, likely forged in the chaos of the Big Bang, could reveal how matter first organized itself into galaxies and clusters. Some researchers even speculate that the whispers encode hints of primordial gravitational waves, ripples from the universe's birth that have faded into near silence. What makes these faint signals so extraordinary isn't just their subtlety, it's their patience. While high-energy cosmic rays blast through space in straight lines, their low-energy cousins wander for eons, weaving through the cosmos' hidden scaffolding like echoes in a cathedral. Every whisper that reaches us is a relic of an ancient journey, a story written in particle trails and magnetic whispers. And as detectors grow more sensitive, we're not just hearing the universe's faintest notes, we're starting to understand the symphony they belong to. Somewhere in the vast expanse of our galaxy, or perhaps beyond it, lurk cosmic powerhouses so extreme they fling particles with energies measured in petaelectron volts, 1,000,000 times more powerful than the Large Hadron Collider's mightiest collisions. Scientists call them p-vatrons, and they're the holy grail of cosmic ray research. The catch: we've never definitively caught one in the act. These phantom accelerators are cosmic ghosts, imprinting their fingerprints on the particles we detect while vanishing without a trace when we turn our telescopes toward their suspected lairs. The hunt centers on a simple but baffling discrepancy. When ultra-high-energy cosmic rays hit Earth, their energy signatures suggest they were cranked up to petaelectron volt levels, PVS for short, by something unimaginably violent. Yet every time we trace these particles back to their origins, the usual suspects, supernova remnants, pulsar wind nebulae, even active galactic nuclei, fall short. They're powerful, but not p-vatron powerful. It's like finding a bullet hole in a wall, but no gun capable of firing the shot. Take supernova remnants, long considered prime p-vatron candidates. When a star explodes, its shockwaves should accelerate particles to PV energies, at least in theory. But observations tell a different story. Even the most turbulent remnants like Cassiopeia or Tycho's supernova max out around 100 teraelectron volts, just 10% of the PV threshold. Some researchers argue these cosmic engines might briefly hit PV levels during their earliest, most chaotic phases, like a sprinter achieving top speed for just a few strides. But without catching one in that fleeting window, the evidence remains circumstantial. Then there's the galactic center, a chaotic zoo of black holes, dense star clusters, and swirling magnetic fields. The supermassive black hole Sagittarius seems like a natural p-vatron, its gravitational tides capable of shredding matter into high-energy debris. Yet when astronomers train gamma-ray telescopes on it, the signals are murky at best. One tantalizing clue emerged in 2021, when China's Lhasa Observatory spotted 12 gamma-ray hotspots near the galactic plane, some potentially reaching PV energies. But pinpointing exact sources proved impossible, like hearing an orchestra's crescendo while stuck outside the concert hall. The implications of finding a true p-vatron go beyond cosmic bookkeeping. These accelerators could unlock secrets about how particles behave under extreme conditions, offering glimpses of physics beyond the standard model. If dark matter is made of heavy, as yet undiscovered particles, p-vatrons might be smashing them together in ways that leave detectable traces. There's even speculation that p-vatrons could be natural time capsules, preserving exotic states of matter from the universe's first moments. New instruments are joining the chase. The Cherenkov Telescope Array, set to become the world's most powerful gamma-ray observatory, aims to catch p-vatrons in the act by mapping the sky with unprecedented precision. Meanwhile, neutrino detectors like IceCube watch for the telltale flashes of particles produced when PV cosmic rays collide with interstellar gas. The strategy is clear: surround these phantoms with so many eyes that they finally have nowhere left to hide. Until then, p-vatrons remain cosmic will owe the WISPs brilliant, elusive, and utterly transformative if ever caught. Their existence isn't just a scientific hunch, it's a necessity, the missing link between the cosmic rays we detect and the unfathomable engines that launch them. Every unexplained PV particle is a breadcrumb, leading us deeper into the labyrinth of high-energy astrophysics, and closer to rewriting what we thought we knew about the universe's most powerful particle accelerators. Imagine looking up at the night sky and noticing something impossible, a silhouette where a star should be, except there's nothing visible blocking the light. Now imagine that happening not with starlight but with cosmic rays. Astronomers call these bizarre absences cosmic ray shadows, and they might be the closest thing we have to X-ray vision for the universe's darkest secrets. These eclipses aren't caused by planets or dust clouds, they're regions where the normal downpour of cosmic rays suddenly drops off, as if some invisible hand caught them mid-flight. The first definitive shadow was spotted in the late 1990s by Japan's Agasa Observatory, monitoring particles streaming from the direction of the moon. Normally, our lunar neighbor should block some cosmic rays, creating a faint deficit in detectors. Instead, researchers found something far stranger. The shadow was deeper and wider than physics predicted, like the moon had grown an invisible force field. The real shock came when similar shadows appeared where nothing should be, casting them patches of empty space where cosmic ray counts plummeted by up to 40%. One persistent void lingers near the constellation Taurus, a cosmic blind spot where high-energy particles seem to vanish into thin air. At first, scientists blamed instrument error or statistical flukes. But as data piled up from observatories in Tibet, Bolivia, and even balloon-borne detectors, the pattern held. The universe has built-in cosmic ray filters, and we have no idea what they're made of. One leading theory points to rogue magnetic fields. Galactic magnetism is notoriously messy, twisted by supernova explosions, stellar winds, and the restless churn of interstellar gas. A chance alignment of magnetic domains could, in theory, deflect incoming cosmic rays like a prism bending light, creating artificial shadows where particles get diverted. But simulations show this shouldn't produce deficits as sharp or sustained as what we observe. That's where darker possibilities emerge. Some astrophysicists speculate these eclipses could be the fingerprints of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. These trillion-ton filaments, thinner than an atom but stretching across galaxies, might warp local space enough to scatter or trap passing particles. Others suggest primordial black holes, the universe's first black holes forged in its fiery infancy, could be drifting unseen through these regions, their gravity wells swallowing cosmic rays whole. Then there's the wild card, antimatter galaxies. If pockets of antistars or anti-nebulas exist, their matter-antimatter annihilation zones would be cosmic ray dead zones, converting incoming particles into pure energy. It's a fringe idea, but the sheer violence of matter-antimatter reactions matches the energy deficits better than most conventional models. The implications ripple far beyond cosmic cartography. If these shadows trace hidden structures, they could reveal where dark matter clumps or how magnetic fields thread between galaxies. New instruments like the Cherenkov telescope array are now scanning these voids at ultra-high energies, hunting for subtle patterns that might betray their origins. Every cosmic ray that doesn't arrive carries as much information as those that do, a negative image of the universe's hidden architecture. What makes these eclipses so electrifying isn't just their mystery, it's their defiance of cosmic transparency. We're used to thinking of space as an empty stage where light and particles move freely. But these shadows whisper a different truth. The universe is layered with invisible barriers, filters, and traps we've only begun to notice. And behind each one, something extraordinary might be waiting. The next decade promises to rewrite cosmic ray science, not with incremental steps, but with quantum leaps in technology so advanced they border on science fiction. At the forefront stands the Cherenkov Telescope Array, or CTA, a global network of over 100 ultra-sensitive telescopes spanning Chile's Atacama Desert and Spain's Canary Islands. Unlike traditional observatories, this next-generation detector doesn't just spot cosmic rays. It captures the fleeting blue flashes they create when striking the atmosphere. Cherenkov radiation with precision down to billionths of a second. The goal: to catch ultra-high-energy particles in the act, tracing their origins with such clarity that long-standing mysteries like the "oh my god" particle might finally surrender their secrets. But the revolution isn't confined to Earth. NASA's upcoming all-sky medium-energy gamma-ray observatory, or Amigo X, will orbit our planet as a cosmic ray bloodhound, sniffing out faint trails of antimatter and gamma rays that ground-based detectors miss. Imagine mapping the entire sky's particle flux in real time, watching how cosmic storms evolve hour by hour. Meanwhile, Europe's JMUSO mission plans to turn the International Space Station into a cosmic ray watchdog, using its orbital vantage to spot the ultraviolet glow of particle showers across continents, an unprecedented scale that could reveal patterns invisible from the ground. Underground, the hunt takes even stranger turns. The Giant Radio Array for Neutrino Detection, or GRAND, will blanket mountain ranges across 3 continents with hundreds of thousands of radio antennas. Their target: the faint static crackle left when cosmic rays or their neutrino cousins interact with rock, a technique so sensitive it could detect particles tunneling straight through the planet. And then there's IceCube Gen 2, the Antarctic detector's successor, which will transform a cubic kilometer of polar ice into the ultimate particle trap, listening for quantum whispers from the birth of black holes. Perhaps the most daring vision comes from Breakthrough Starshot, which aims to launch microscopic probes to nearby stars using laser propulsion. While not a cosmic ray mission per se, its light sail technology could inspire space-based detectors far beyond Earth's protective magnetic bubble, floating observatories drifting between planets, free from atmospheric interference. Picture this: a swarm of sensor-laden nanoprobes scattered across the solar system, triangulating cosmic ray sources with interstellar precision. What ties these experiments together is a shared ambition: to stop treating cosmic rays as isolated anomalies and start seeing them as interconnected threads in the universe's grand tapestry. The CTA might pinpoint particle accelerators near supermassive black holes, while Amigo X deciphers how those particles interact with galactic magnetic fields. GRAND could uncover hidden links between cosmic rays and dark matter, while IceCube Gen 2 tests whether neutrinos are the missing messengers tying it all together. The challenges are as staggering as the potential. Some detectors require superconductors cooled near absolute zero. Others demand AI capable of sifting exabytes of data for a handful of meaningful events. But if even a fraction of these missions succeed, we'll be staring at a new cosmic ray paradigm, one where every particle tells not just its own story, but reveals the invisible machinery shaping the cosmos. The future isn't just about better detectors, it's about rewriting what we thought we knew about the universe's most elusive particles. And with every new experiment coming online, the pieces of that puzzle are falling into place faster than ever before. From the oh my god particles' impossible speed to the Antarctic anomalies' upward blasts, from cosmic ray shadows cast by nothingness to P-vatrons lurking unseen, we've journeyed through 25 of the universe's most baffling particle puzzles. Each one defies expectations, cracks open new questions, and reminds us just how much remains hidden in the void. These aren't just scientific curiosities, they're cosmic breadcrumbs leading us toward revelations that could rewrite physics, redefine origins, and reveal forces we've yet to name. Consider what ties them all together, a thread of mystery so persistent it's almost poetic. After a century of study, we've mapped galaxies, glimpsed black holes, and unlocked the quantum realm, yet cosmic rays still outwit us. They arrive without warning from nowhere and everywhere, carrying energies that shouldn't exist, pointing to sources we can't see. They bend time, pierce planets, and whisper of dimensions beyond our own. Even the detectors we build to catch them, ice-bound arrays, mountaintop observatories, spaceborne sentinels, feel like desperate attempts to eavesdrop on a conversation the universe never meant for us to hear. But here's the thrilling part: every unanswered question is an invitation. The same cosmic rays that frustrate today's scientists will inspire tomorrow's breakthroughs. Maybe you'll be the one to decode the galactic ghost ray's origins, or prove dark matter's role in the positron excess, or finally catch a P-vatron in the act. The tools are coming: hypersensitive neutrino detectors, AI-driven sky scans, even lunar observatories free of Earth's atmospheric static. The next great discovery might already be hiding in data we've yet to analyze, or waiting for a fresh pair of eyes to see the pattern everyone else missed. So stay curious, follow the research, watch the skies, and embrace the beautiful irony of this field. The more we learn about cosmic rays, the more they humble us. They're not just particles, they're teachers, and their ultimate lesson is clear: the universe is far stranger, wilder, and more wondrous than we've dared to imagine. The next chapter is yours to explore. Keep looking up.